Today we are looking at the topic of bilging amidship. So, and a box-shaped vessel, which is very easy to work on. So, assuming that our ship is length long, like this side to this side, it's length long, and it is immersed in water with some draft of D underwater, and what it has, it's some first, second, up to that, and there's a mid water compartment. What else do we have? This is a side view of our ship, so it's this thing. And now what is happening? Our ship get bilged, or there is a hole here. So if there is a hole here, what is going to happen? Water is going to flood in. So on this small middle apartment, it will be filled with what? It will be filled with water. What is happening with this water? This water, what it does, it's getting in our ship till it fill all this apartment, this mid apartment. Then our ship, because of water in, it loses something called buoyancy. A buoyancy is a force that keeps ships, or should I say every floating object floating. Okay, so it's kinda push out the water, and that's it keep it floating. This is just simple for a force of buoyancy. So if water comes in, the water is supposed to be outside for it to let the ship float. So if the water comes in through that hole to that water compartment, it's now lost buoyancy. So if buoyancy is lost, so our ship loses a force that makes it float. Remember that our ship is didn't change its weight. It didn't change its weight. Remember, if for a ship to float, two forces are balancing each other. Obviously there is there are two forces that balancing for a ship to float. The first one, obviously, it's going to be G, gravity pulling down, and it's going to be buoyancy pushing it up. Okay, these forces should always be equal for a ship to float. Okay, so just because water went in, meaning we have lost buoyancy. So for a ship to continue floating, buoyancy and gravity need to be the same. Should I say buoyancy and weight need to balance each other for a ship to float. So because of water just dived in, so there is some buoyancy lost. So for us to keep the ship afloat, what do we need to do? We need to regain the lost buoyancy. Okay, because there was no loading or unloading in the ship, meaning the ship has the very same weight. So because of loss of buoyancy, and this one does not changing, and what is happening, the ship is going to sink. So we're just going to record a second draft. A ship is going to sink. The ship sink because it lacks buoyancy. In basic English, it just lost some buoyancy. The buoyancy lost is going to be substituted by these So the buoyancy that we just lost through a hole or a bilge that just happened is going to be compensated by these other compartments that are intact meaning no water coming in. So these ones which are not bilged or not having a hole, they are going to serve as our buoyancy gained. Since the ship lost buoyancy, we just said it's going to sink, it's going to have experienced a change in its draft. So a change in draft are just represented in this case as as an X. So a ship is going to sink few meters. So for us to know if we still have enough freeboard, yes, we still have enough freeboard, we need to know how much a ship is going to sink if it is built, or if there is a hole in that developing and water coming in. remember, just because water here are coming in and out, this water that just went in do not serve or do not add any part on the weight of the ship. This serve as this is just a part of the ship that is lost. It's no longer part of our weight and it's no longer part of our buoyancy. So the kb of our ship is not going to change, or should I say the weight of our ship is not going to change. What else? We are to know how much we are going to sink, we need to know also how the length of our compartment, midship compartment, of which I call it length 1. The length with big L is for the length for the whole ship, and L1 is for length of the midship compartment that is bilged. So because we want to keep our ship afloat, or we want to keep our ship floating, we need to conserve buoyancy. So we need to keep buoyancy not changing, even though we just lost buoyancy, but we need to keep our buoyancy the same. So that's why we're going to compensate with other buoyancy gains. So in simple terms, I meant to say, for a ship to continue floating, it needs to conserve its buoyancy. So what it means to conserve buoyancy, it simply means that buoyancy lost should equal to buoyancy gain. Okay, what is the buoyancy that we just lost? We just lost the buoyancy for the midship compartment. So we just lost L1, the length of this midship, times draft, our initial draft, times what? Times the breadth of the ship. Remember, ship is in 3D, so we still have something else, B here. So times that B. The lost buoyancy should equal to what? To the gained buoyancy. What is gained buoyancy? We said gained buoyancy, it's only these two parts. These are gained buoyancy. So to get the volume of these gained parts, we're just going to say volume of from here to here minus the mid part, of which water will keep flowing in. So exactly it's going to be x for height times length of the ship, the big L, times the breadth of the ship. Then because we only want for the parts on the side, or should I say on the end after and up after the ship, so we're just going to subtract what? The volume of the mid part. The mid part is what? Legal length, or should I say the length for the compartment, I call it L1, times or volume times x, this x for the height, times the breadth again. So we'll do some math, distribute the negative inside. I'll just going to lend this to this step. Then here we still have this one, L1D and breadth. So here we do have a common factor. We do have a common factor of x and of b, but I chose to take x in this case. X. Then how do we left with? We left with what? We left with L length times breadth. Okay, minus what do we left here? Small length times breadth. So remember our x here, we said it's going to be our change in draft, or should I say the sinkage for our scenario. So the sinkage is going to be x, and we just took all this out. Then we can find, or should I say we can make our sinkage subjects of the formula. So we're just going to divide both sides by this. So we're just going to land with what? Just going to land with x. X now is going to equal to this one divided by this, of which is L1 times initial draft times breadth of the ship, all over what? This one we divided. Okay, then it's L times the big L for the ship, BE, minus L1 times B. So from this, there's something that we can notice. L1 times D times, should I say length of the ship, and what's this? Length of the whole ship, its draft and breadth. What that gives us? It's a volume. Volume what? Oh, it's the small length. Then this length and what? Draft, the height, and what? And the breadth. That gives us the volume of what? Of the last buoyancy. So now we can deduct from our math that the sinkage is going to equal to length d, b of which is the last buoyancy, volume of the last buoyancy, all over, what is this one on the denominator? To understand this on the denominator, I'll need to do another drawing of the ship looking at the top view. Assume this is our boxed ship vessel. This is our boxed ship vessel. So this is going to be our B for breadth, and this one is going to be the length of the ship itself. Length, I should have used L, and this one is going to be from here to here, it's going to be the small length. So length times breadth, the big length, is going to be the area of the ship. So if area of the ship minus what? Minus the area of this one. So it simply means that it's the area of the intact water plane area. The intact one, this one is not intact, it's the bilged one. So the intact, it's the rest of the area that has no water. So it simply means that to get the sinkage, you need to get the volume of the last buoyancy, which is this numerator part, and on the denominator, it's area of the intact water plane. So it's simply, it's intact water plane area. So to get the sinkage of the ship after bilging, we need to take into account volume of the last buoyancy over intact water plane area. This is how the formula of sinkage is born. It's simply read as the sinkage is equal to volume of the last buoyancy over an area of an intact water plane area.